Okay, thank you. Right. So let me just begin. Last time we started to learn about the light interaction with dielectric particles. So what that means is that we wanted to describe the behavior of scattering by a small dielectric particles, and if the particle is sphere, like perfect sphere, then we can obtain the exact solution of this scattering phenomena. And the way we do it is we divide our solutions, electromagnetic field solutions, into a spherical harmonics, and then apply the boundary conditions to match the electric field and magnetic field components at the boundary of the sphere. And so the solutions can be interpreted like but as a result of it, we obtain a series solution. And then series solution means that the interpretation of it is that we can interpret it as a dipole component, quadrupole component, and octupole component, and so on. So as L increases, you have your multipolar component have more number of poles. And then this is pretty general behavior of a radar cross-section of a nanoparticle as a function of its size with respect to the wavelengths of the particle. And as I said, when the size of the particle is large enough, like much larger than lambda, like 10 to the 2, like 100 times larger than it, that the radar cross-section converges to the actual physical area of the particle, right? And then on the other hand, if the particle size is very small, so that the size of the particle is actually much smaller than lambda, then the radar cross-section is actually proportional to the force power of this particle size. Okay, in this regime is called Rayleigh scattering regime, and in the middle, of course, the response of a particle is a bit complicated, so there's no simple theory to explain this regime in the middle. Okay, so in order to explain the Rayleigh scattering regime, what we did was we apply electrostatic approximation. Even though electromagnetic fields are oscillating in space, because particles are very small, we can ignore the phase difference between like within the particle, because the size of the particle is much smaller than lambda. So the phase difference within the particle, phase variation, can be ignored, which is called electrostatic limit. So we can just use a simple Laplace equation. And the solution of this equation is even very easy. So you have R and theta equation, and even though you express things in series, like the series of Legendre functions, but if you actually apply the boundary conditions, you realize that you only have like very few number of terms. So for instance, the inside of the particle, you have only one term, and then outside of the particle, you have two terms. The one left is the incident wave, and then the one on the right is the scattered wave. Okay, and the scattered wave has a form of a dipolar field. So from that, we can obtain dipole moment of the particle due to the applied electric field. And by taking the ratio of these two, you can obtain polarizability. And then from the polarizability, you can obtain scattering cross-section. And here you see that the scattering cross-section is actual particle area, particle physical cross-section area, like pi a squared, multiplied by 2 pi a over lambda fourth power, right? So this tells you that if the particle size is small enough, then the scattering cross-section is proportional to the fourth power of the size of the particle, right? Okay, so Rayleigh scattering explains why the sky is blue and sunset is red, and why we see this red sky or yellow sky in the when there are a lot of dust in the air. Okay, because too much scattering, blue lights all gone. That's what happens. So what we learned today is a little more complicated phenomena, because what we learned so far is pretty simple. Like when particle is very, very small, so that everything is in the Rayleigh scattering regime, then the scattering cross-section is just proportional to the fourth power of the particle size. That's it. It's too simple, right? But there are the region where things are a little bit more complicated. So here I'm showing you the response. So y-axis is the scattering cross-section of a AU nanoparticle, gold nanoparticle with a radius of 100 nanometers, and right you have the same size particle but made of silicon. Okay, and as you can clearly see, the response of silicon nanoparticle is much more complicated than the response of gold nanoparticle, right? So many peaks in case of silicon. And if you look at the size of the particle, 2 pi lambda, 2 pi a, so a is the wave, the radius. 2 pi a is about 600 nanometers, and here also 600 nanometers. So it's about the size of a wavelength, right? It's slightly bigger, but anyway, it's about the size of the wavelength. So things are become complicated from here. So why these are so different? The first reason is that in case of gold nanoparticles have so many free electrons, right? So that the response of gold nanoparticles are mostly electric. So you have a oscillating electromagnetic wave. So electric field is oscillating this way, magnetic field is oscillating that way. Then this guy has so many free electrons. So this one tends to be electric dipole, strong electric dipole, right? So its response is mostly electric. So there's nothing too much interesting here. But in case of silicon, the electrons in the silicon is a bit, first of all, the carrier density is low, and also its response is a little more complicated. So in this case, you have like multiple responses appear. And here the peak 1, peak 2, peak 3, peak 4, peak 5, and so on. And then as you can associate each peak to their different origins. So the first peak, the longest wavelength peak, can be associated to the magnetic dipole oscillation, resonance. And then this one is electric dipole resonance, magnetic quadrupole resonance, electric quadrupole resonance. Okay, so as we learned before, the response of a nanoparticle to the incident electromagnetic wave can be decomposed into multipolar expansion, like multiple components, like a dipole, quadrupole, octopole, and so on. And here we have dipole components and magnetic electric dipole components and magnetic electric quadrupole components. So before we jump into detail, do we have any question? Okay, Kim Chae-yoon asks, can doping concentration of semiconductor affect the total scattering cross-section of the sphere? Yes, this is a nice, very nice question. In principle, of course, the doping concentration of semiconductor affect to total cross-section. But in order to see a significant difference, you have to dope this, silicon a lot, right? And because you probably remember, so what's important is the plasma frequency. And plasma frequency, you remember there was an n, there was a square root n. Anyway, there's a dependence on the doping concentration. And then when doping concentration is too small, then this plasma frequency lies in the far infrared, so that it can only affect the response at that regime. So in order to see some difference in the visible frequencies, you have to dope a lot, okay? But yes, in principle, it affects. And then its dipole and quadrupole is same as the thing at page 8. Yes, this is the same thing that we discussed in the previous lecture slides. So this is pretty general. So you probably are familiar with in your electromagnetism class. You're familiar with solving a boundary problem. Like let's say you have a boundary like V equals V0, and then here say V equals 0, and then try to solve this V, X, Y everywhere. If you have this type of a problem, what you do is you try to expand V, X, Y as a linear combination of a cosine and sine series, right? Cosine and sine series of x-axis, and then try to match the boundary conditions in order to get the full series solution. So that's typical way we solve the problem in Cartesian coordinates. And then here, the spherical case, this multipolar expansion is pretty generally used. Okay, so not only in electromagnetism, but also in quantum mechanics and all the other like wave phenomena, this multipolar expansion is generally used. Okay, so why the magnetic resonance is important? Why? So people has ignored this the importance of this magnetic resonance until recently. And then they got interested in this magnetic resonance like from like late 2010 or 2000, yeah, just a few years ago, like 5 years ago. And then why people got interested in this is because it can induce many non-intuitive phenomena of scattering behavior. So for instance, like if you have a silicon, as I said, silicon has a really high index, and so magnetic dipole occurs when you're just, so if you think about the electric dipole, it's pretty obvious, right? Electric dipole is just the oscillation of the electrons going back and forth along the direction of the electric field. And then magnetic dipole, when you have a oscillating magnetic field, in order to obtain, create this dipole moment, your electrons in the material, in the particle should oscillate, should rotate back and forth, right? In order to create vertically oscillating magnetic dipole. So in order to induce magnetic dipole resonance, the size of the particle is very important. So size of the particle must satisfy like this type of a relation in order to get the resonance, right? So what I mean by resonance is if you look at this particle from the top, so then your magnetic resonance is going back and forth like that. And then you have oscillating electric field looks like this. So the path length of this circular oscillation is, of course, is about like 2 pi a, right? And then you have to and then you have to match. So what in one oscillation they have to be in phase in order to induce a resonance. So this must be similar to the size of the wavelength. Okay, so that's the condition for the magnetic dipole resonance. And here index n tells you about basically the contraction factor for the wavelength. So if your particle is high index, the wavelength becomes shorter, right? So that you can obtain magnetic dipole resonance with smaller particle. So that's another thing that you need to keep in mind. So here, again, sub-wavelength nanoparticles can have magnetic dipole resonances if n is sufficiently large. So with large n, the wavelength of electromagnetic wave is much shorter in the material, so that even if the size of the particle is small, you can still have a magnetic resonance. Okay, so then what makes it interesting? Oh, before then, so people start to look at high index material for that reason, like in order to induce magnetic resonance with sub-wavelength nanoparticles, we need a high index material. So people start to looking at high index materials like this. And this chart actually I showed you before, right? And yeah, so what's the usage of it? Well, magnetic resonance compared to the electric dipole resonance, magnetic resonance have more, basically have your electric field more confined inside of the particle, like inside of the particle, so that you can have a strong confinement of an electromagnetic field. So what we can do with strong confinement of the electromagnetic field is basically a you can enhance non-linear behavior, like third harmonic generation. I'm not sure how many of you are familiar with third harmonic generation, but it's like this. You have a photon, light with frequency omega. Then there are very, very low chance that, 3 photons in, 1 photon out with different frequency, like 3 omega frequency. So this is called third harmonic generation. Okay, and then this type of non-linear behavior can be significantly increased at magnetic dipole resonance. So that's what this chart shows. And here also you can also use it to enhance Raman scattering. And I guess many of you heard of Raman scattering, right? Raman scattering is like this. You have a incident light in with omega, frequency omega. And then your material, basically your sample, have various vibrational mode. Okay, so this wave excite some vibration, okay, vibrational mode with frequency capital omega, and then your outgoing wave should have omega minus omega, right? or omega, there's a small chance that you have omega plus omega if you do in this way, but it's less likely. So by measuring the difference between the input and output wave frequency, you can identify what's the characteristic vibrational modes of the material, and that's called Raman scattering. This process is called Raman scattering, and this process is also a second order process, like a non-linear process. So if you have a strong light confinement inside a nanoparticle, then this process can be enhanced a lot. Okay, so you can see Raman enhancement is more than 100 times. And similarly, this can be applied in other types of a non-linear behavior. And so people got interested about this. Okay, but other than non-linear behaviors, there's another interesting phenomena that I would like to mainly focus on in this lecture. So before then, do we have any question? Is there any question that you want to ask? Nothing? Okay, then I will try to move on to the scattering behavior of high index dielectric nanoparticle. So as I showed you before, high index dielectric particles like silicon here and there tends to have both electric dipole and magnetic dipole, right? So that their scattering behavior is a little complicated, right? It has two peaks basically. But we want to move like one step further into the system, and then we want to divide the scattering components, scattered light components, into two. So the first component is forward scattering, right? How much of the light is scattered forward. And then this blue is how much of light is scattered backward. And then if you add them up, of course, it becomes the total scattering, right? So this is the chart. So forward scattering and backward scattering, and here is the forward to backward ratio. Okay, the orange curve is the forward to backward ratio. And as you can imagine, both forward and backward scatterings have two peaks, right? Well, that's easy. That's what you can easily know. But what I would like to emphasize here is that the position where the backward scattering is peaked and the position where the forward scattering is peaked is a little different, right? And because of that, if you take the ratio of forward and backward scattering, they have very different behavior. So if you look at this, if you are on this side or that side, the scattering is mostly forward, right? So forward to backward ratio is larger than 1. Whereas if you are in this regime, in the middle, your scattering becomes mostly backward, right? So I just want to explain, just try to explain why this is happening, and why this is important. Okay, so as I said earlier, like in back in like long time ago, when we have this simple scattering picture, it seems like in the Rayleigh regime and like, you know, your scattering forward and backward are always isotropic. And then if you go to a large, and then as your particle size larger and larger, your scattering becomes keep going like forward, keep towards forward, right? So seems like based on this chart, it seems there's no way to control the scattering direction, right? But what you observe here is that even with the same size of the particle, the scattering direction can be vary a lot. Like it can be almost 100% forward, but it can be like very backward, or it can be forward and backward become the same. So I just want to tell you why this is happening. So if you look at the so this is the schematic, the axis that is aligned with these figures. So E field direction is along X, and then H field direction is along Y, and then propagation is along Z. Now, if you look at this point where forward and backward resonance amplitude becomes exactly same, if you draw the scattering pattern, you see this. Okay, you can see backward and forward scattering are identical, like they are very symmetric. So, and based on this resonance, can anyone say whether this is electric dipole or magnetic dipole? Can anyone guess whether this number one is electric dipole or magnetic dipole resonance? Electric dipole. 정명근 said electric dipole. Why do you think so? Why do you feel like this is an electric dipole? Similar picture at page 18. Okay, yeah, this is very nice observation. Yes, so what I wanted to expect, what wanted to hear was that, you know, electric field is along X direction, right? And then this one is donut with the hole punching through X axis. So this is how a X aligned resonance, X aligned dipole emission pattern, right? And then if the dipole is aligned to X axis, then it must be electric dipole, right? Because it's the direction of the electric field. So that's what we wanted to say. And for this, with the same analogy, if you look at this one, the scattering pattern number 3, you can see here a forward and backward scattering are also balanced. But in this case, this scattering pattern is due to the oscillation of dipole along Y direction, right? So Y direction is a magnetic field direction. So this should be due to the magnetic dipole moment, right? Due to the oscillating magnetic dipole, right? So this and that is basically at the top, at the very exact position of electric dipole resonance and magnetic dipole resonance, right? You can see also the amplitudes are peaked at each position. The question is this and that. So here, in between the electric dipole and magnetic dipole, your resonance becomes mostly backward. And then if you go to this regime, your resonance becomes mostly forward. Can anyone imagine why this happens? Why we have a strong forward or strong backward resonance depending on the frequency, like depending on where we are at with respect to the resonance position. Due to the resonance, well, everything is due to the resonance, right? Everything is due to the resonance. Like, this is also electric dipole resonance, and this is a magnetic dipole resonance. So, if you say due to the resonance, then it's kind of too broad to explain things. So let me try to explain. Try to explain this thing. If unless you have any good idea, or yeah, maybe I'll keep this question unanswered, but I'll probably answer it in a few slides later. Okay. So anyway, this is the general behavior of how a high index dielectric nanoparticles have scattering pattern. And now this is an auxiliary slide about how your scattering pattern changes as you change the shape of the nanoparticle. And here what we are actually looking at is we see the same plot as we saw as we change the vertical length RZ of the nanoparticle become smaller. So we basically squeeze the nanoparticle along the vertical direction. And as you can see, as you squeeze the squeeze the nanoparticle, the electric resonance position changes, but not too much, right? But the magnetic resonance position, it's a 620, 580, like 550, and so on, like almost 500. So it's going rapidly moving towards the shorter wavelengths. So why does this happen? Like why, as we squeeze the nanoparticle, why magnetic resonance affects more than the electric resonance? So that's also can be understood based on the resonance. Like if you look at how the resonance occurs. So electric resonance, if you look at this, is occurring along x direction, right? So as you squeeze the particle along z direction, if the top view of the particle doesn't change, right? It's Rx, and then Ry remains the same. And then we are in electric dipole resonance, we are talking about electrons oscillating along x direction. So even though we squeeze things in along z direction, of course it's going to be affected, but it's not strongly affected. Okay, but if you think about the magnetic resonance is along y direction, right? And then in order to have oscillating magnetic field, as I said, you need circulating electric field, circulating current. So your circuit is basically along x Z direction, right? So you have circulating current. So as you squeeze the thing, you're basically making your circuit more and more squeezed. And so the effect of this deformation is much more drastic compared to the effect on the electric resonance. So that electric resonance, I mean, magnetic resonance move more rapidly compared to the electric resonance. So like in here, even they are almost, like merged. Electric resonance and magnetic resonance are almost merged. And then this merging of electric resonance and magnetic resonance condition is called a Kerker condition. Kerker, Kerker condition. And here in the Kerker condition, you have unidirectional scattering. So what I mean is that this is basically the answer to the question that I raised in a few slides ago. So now let's look at the electric dipole. So let's think about the electric field due to the electric dipole oscillation. Then the electric field having this direction, right? So in case of left, so here and there, the electric field are pointing at the same position along like a Z direction, but like along X direction, for instance, they have opposite direction, right? Left and if you compare left and right. And then if you also think about the magnetic dipole, you have an oscillating magnetic dipole, and then think about the electric field associated with, you can see here, it's exactly opposite. Like if you compare left and right, they have different direction in terms of on Z axis, but they have the same direction in terms of a X axis, right? And then assuming that you're on the same side, like these electric dipole resonance and magnetic dipole resonance are combined. Then what happens is that you have here, like on the right side, this and that have the same direction so that they are amplified, right? On the other hand, this region and that region, this one wants to go counterclockwise, but this one wants to go clockwise so that they cancel each other out. So there's nothing here. So as a result, you have a strong forward scattering, like almost 100% forward scattering in this case. So that basically explains why, why we have strong forward scattering in this regime, right? But then why in this case you have strong backward scattering? Now I guess you can answer this question. Like, why is that? I guess some of you may kind of have an idea, but probably having some difficulty to explain it, like write it into a clear statement. But let me just tell you the answer. The reason is, at the resonance, your phase is basically flipped by 180 degrees. So what I'm telling you is that let's say this is electric dipole, and this is magnetic dipole. If you're on the same side, okay, so this position is longer wavelengths compared to the magnetic dipole and also the electric dipole, right? And then I guess you remember, depending on the frequency, if you have a resonance, your response changes from 0 to pi, right? You remember this, right? So because we are on the same side, so the phase of electric field and magnetic field, electromagnetic fields due to the electric dipole and magnetic dipole have the same phase, right? So, and then in that condition you have a forward scattering, and then backward component is cancelled. But in the middle, it's like electric dipole is in this regime, whereas magnetic dipole is in this regime, right? Because it's right side of the electric dipole, whereas it's left side of the magnetic dipole. So that magnetic dipole direction is basically flipped. So what happens is that now the backward propagation is enhanced and forward propagation is suppressed, right? So this is how you understand, this scattering dynamics. And then people realize that, okay, oh, this is really nice. Because another thing that I would like to mention is that in order to obtain a perfect forward propagation, the amplitude of the electric dipole response, and amplitude of the magnetic dipole response must be the same, so that they can cancel out completely, right? So that's another consideration. Even though the electric dipole and magnetic dipole is matched, the cancellation can be imperfect if the amplitudes are different. But anyway, this is a very nice way to obtain a transmissive meta surface. Okay, if you want to obtain a optical element that is highly transmissive, but if you still want to obtain get some phase response, then this Kerker condition it can be used in a very useful manner. And there's more complicated combinations also, like there's what is called anapole mode. So anapole mode is the combination of electric dipole and what is called a toroidal dipole. Toroidal dipole looks pretty complicated. Toroidal dipole looks like a toroid. So you remember that in a toroid, magnetic field is oscillating. Circulating. So if you have a circulating magnetic field, which looks like a blue curve here, you have a electric field looks like this. And then if you look at the field outside, here, field outside, let me be more clear. Here it's going clockwise, but it's going counterclockwise, and also it's going clockwise, counterclockwise. So field outside is canceled. But if you look at the field inside, they actually, if you look at the electric field, they are amplified, so that you can basically obtain a strong electromagnetic confinement inside the nanoparticle. Okay, and there's no outside field, so it's like a strong localized resonance can be obtained by anapole creation. And there's another thing that you can expect is that if you have a multiple nanoparticles close to each other, then what happens is that they want to make some sort of an ordering, anti-ferromagnetic ordering, because it's energetically favorable. So you can just you can just if the interaction between the nanoparticles are strong enough, you can actually see optical antiferromagnetic ordering. And there's another thing which is called bound states in the continuum. This topic is also very recently raised. And what this is like this. You have like continuum mode. What I mean by continuum mode is that you have a freely propagating mode. But if you combine like kind of two freely propagating modes, right? Both of them can have a outside radiation, but you can see like in the anapole mode, you can make their wave cancel each other in the outside of the particle, but have a strong field enhancement in the inside, so that you can create some cavity mode that is called bound state in the continuum. And then if you have a bound state in the continuum and then making your bound state a little bit incomplete, which makes you a quasi-bound state, then your localized mode can now couple to the free mode, free space, so that you can actually start to absorb it. It's a bit too complicated, but anyway, this is a really important new topic. And then this involves all like, this symmetry thing and topology discussion combined. So I just don't want to go too much into the detail, but if you have any question, please ask. But in any case, I hope you got the point, right? Like the point is the electromagnetic or scattering response of a dielectric nanoparticle is very important. And then that response can be explained in most cases by decomposing their multipolar response, like dipole, electric dipole, magnetic dipole, electric quadrupole, magnetic quadrupole. If you and then you can explain things based on the linear combination of those responses. Then you can do these relatively non-intuitive stuff. Okay, so if you have no question, oh, this is it. So yeah, so you really don't have a question? Then I think I'll move on.